how to graph this stuff. We've learned what residuals are. We have learned about linear correlations, and so on. Well, we had a couple days ago, something happened. You guys listen up. A couple days ago, look. There was a pattern in the residual plot. So then we said, whoa, a linear model is not appropriate. And then we stopped right there.
Oh, we said yikes.
So it was a cliffhanger. You know, we said, yikes, a linear model is not appropriate because there's a residual plot pattern. So now what? Today is the answer to that. So what we have to do is transform the data. Yeah, we do not have to do that. But we are going to transform the data to condense it and to make it linear. Okay? So what's happening here is we're going to do one type of transformation. There's only a limited amount of transformations that we have to learn how to do, and then we get the feel of how to do it, and we're good. But I want to first talk about exponential transformations. An exponential transformation happens if you have data like up here, okay, and it's increasing very rapidly. Much more than just a parabola, much more than just an x squared. In fact, what makes it exponential is that it's something with an exponent, with a variable in the exponent. Okay, so it's increasing very rapidly. That is called exponential growth. Exponential growth. And so then here, likewise, you can have a very quick going down. That's exponential decay. Close. Exponential growth and decay. So there's this thing that you learn in pre-calculus, and you actually first learned about in Algebra 2. So if all you've had is Algebra 2, then you have experienced this. That's logarithms. And those are kind of a tricky, seems kind of worthless, computational maze. But what I want to, I want to put it into more real terms. And what a logarithm is going to do is condense the data so that it's shrinking and condensing all the y's, which that then straightens it out, is what happens. So, in summary, I'm going to tell you what we're going to do, and then we're going to do it. First, we have a set of x's and y's. We put it in, we graph it. We looked at the data set, and it didn't really look quite linear. Looked like it had some kind of curve. We used the residual plot and knew a linear model was not appropriate. So then we're going to do the only transformation we know of so far, and that is we're going to transform the data. We will keep the x's the same. We will not condense in the x direction. We're going to just condense in the y directions. So we are going to then graph, instead of the y's, we're going to graph the log of the y's. And then we have to check that. So then we have to check the residual plot of the transformed data to see if that transformed data is linear. Okay? We eventually have to work our way back to a different equation, but that's not today. So today is just the calculator process of that. So, let's take a look at our data here. We are going to get in a habit of always putting the same thing in the same lists, so we are always able to remember what's in the correct list, okay? I want us to always put the x's in the L1s, okay, that's natural, and the y's in the L2. That's all good, natural. I've been there, done that. I've been having you put the residuals into L3. But I want us to transform the L3s and the logs. We're going to end up putting the condensed x's in L3 and the condensed y's in the L4, which means I'm bumping your residual placement to L5. If we keep doing those same ones, then we are always consistent and we know what's in each list. It's not a question each time, okay? Now, FYI, we're going to practice doing this little piece right here, but we will not use log of x's until Friday, okay? But we know when we do, they're going to be waiting for us right there in L3. Okay, so here we go. Put this data into your L1 and L2. Do that now. You probably want to clear your calculator first. Don't forget to second plus 712. Okay, you want to do your second plus 712, which then has a little annoyance of you're going to have to put your diagnostics back on under the second zero. Okay. This has the benefit of making sure you don't have old data in. That would be messing you up for some weird reason. Okay. The first half of this problem is no different from what you've already done. Just going to kind of simplify it, but we need to make sure we label our axes very well. So we want to first graph it. We've already done this. What is going to be on our x-axis, content-wise, context-wise? Fry time. This is about the fry time of potato chips and the moisture content that's in them. And I'm going to put a little parentheses FT right here because I'm about to start abbreviating it FT and not have to write fry time all the time. What is then the response to that fry time that we're interested in? The moisture content. Okay, and I'm going to start abbreviating that as MC. Okay, so let's graph that. We've got our x's in L1, our y's in L2. So second y equals, to look at it. If you have cleared your calculator, then you probably have this stat plot off. You need to turn it back on and make sure that you are going to be graphing L1 and L2. Okay? And then zoom 9. And there you go. So I can see a curved pattern here. So I'm going to take a moment, make sure you can get to this point. If you are good to go on that, go ahead and put that into your calculator. Or, I'm sorry, draw that in. I am not making you put the scale on these because that's just some tediousness that would just kind of waste time at this point. Okay. Questions on getting that? Okay. So now we want to graph this residual plot. So I want to put the axes in first. We know that a residual plot has our y-axis and we have the prediction line across there. Now, what x values am I going to be putting on this one? Same thing, fry time. This is still going to have fry time on the x-axis, but what is going to be on the y-axis? Good. The resids of MC. So just put resid. And there's a reason you can't just put resid because we're going to have resids of different kinds of things throughout this process, okay? So I defined that I'm having residuals of the moisture content. Okay, so we need to look at that. In order to be able to do this, I have kind of given you steps. Look, this is a reminder. Don't forget to stat calc your equation for L1 and L2, and then put those resids into L5. Okay? So don't forget to do those two things. So here we go. Stat, over to calc, number 8. I want to tell you something real quick because something's going to come up that's different. When you look up here at my calculator, I have nothing behind linreg a plus bx. Well, this is going to default to finding the equation for list 1 and list 2. If I'm ever wanting to find the equation for another list, which we will be doing today, I'm going to be doing L1, comma, whatever. And today we're going to be doing L1 and L4 later. Okay? But for now, if you do not have those in here, then it defaults to L1, L2, which is what I want right now. So there is our equation. So we're going to write that. And this is predicted what? Good. It's predicted moisture content. Okay? So we've got predicted moisture content is 11.08 minus, and I've lost oh wait, oh here it is, okay. Minus 0.195 times fry time. And it had a correlation of negative 0.9275. Now, incidentally, if you saw a negative 0.9275, what would you think about that linearity? Yes, strong negative linear correlation. Okay, well, guess what? That's why you have to look at the residual plot, because when we go and look at that right now, in order to go look at that, I have to put my residuals into L5, so let's do that. Go all the way over. I know we're skipping over L3 and L4. We're going to put something in those shortly. Over here in L5, second stat. Okay, right now, people, if you don't have a number 7 showing up with resid, what does that mean you have neglected to do?
You didn't do your equation.
Okay, you did not do that right there. You did not get your calculator thinking about a line. Okay, your calculator is thinking about a line if you did the equation. If you did not, then it's just sitting there. It has no line to do residuals off of. But I did that, so here we go. Enter, and there are the residuals. So let's look at it. I want to look at L1 and then what? L5. Zoom 9. Okay. So, boom, there's a pattern there. Let me fill this in, and then I'll come help people who are having a calculator issue. Okay. Here we go. All right, so to this point, we have already done all of that part. So we determined, is a linear model appropriate? Is a linear model appropriate? No, because what do we say?
Yikes.
Yikes. Yikes. Yay. Yikes. We say yikes. There is a pattern in the residual plot. So, man, that good R value was so deceiving. Okay? Okay? Therefore, linear model is not appropriate, which we actually just answered here when we said no. All right. So then let's see if we can fix this. We are going to go through the transformation of condensing the y's. In order to condense the y's, we're going to take the log of the y's. We are going to end up leaving the x's as x's. Okay, so when I end up graphing this, I want to leave the x's as x's. You need to put length here. You're going to leave the x's as x's. However, I am not just going to have... Oh, wow. Sorry.
Okay.
Other problem. Okay, I'm in another problem. Okay, fry time, sorry, and I could have just put FT. Okay, and then my y-axis is what? Good, it is log of moisture content. It is not just moisture content, it is the condensed moisture content. So, I'm going to teach you how to get that in your calculator, in your lists. So come over here. Let's fix up L3 and L4. Now you remember from here what I said I want to go in L3 and L4? Log X into L3, log Y into L4. And we're going to do that all the time. So let's do L3. I put my little cursor up there on top of the L3. I press the log button, which is next to the 7. And I need to do the log of which values? L1. So second, 1. And then, boom, it gives you those ones. Okay? show you, I'm going to tell you where the heck those numbers come from here. I'm going to show you that in just a second. Let's go ahead and log our L4. Our L4 is log of which ones? L2, because I want to log the Y's. Here we go. Now, good job. What I want to do real quickly is talk to you about where the heck these numbers come from, because I do not, L2 for that. I don't like just getting answers and not knowing where it magically gets these numbers from. So here's what happens. If you have log of x equals y, there's an understood base 10 right here. So when you used your log functions and you did those in Algebra 2 and pre-calculus, here's what happened. You went base 10 to the y power is what you get for x. Okay, so here's what's in our list. We put 10 to the L3 power. I know we have put log it to the L3 power, and then basically, and then that's what gives you an x. So watch this. That's what gives you L1. Sorry. Yeah, this is here's where it comes from. If you're interested, you don't have to totally be focused in on this. So here, watch this. Ignore L2 for right now. Just look at L1 and L3. So here's what's happening. Base 10 and look at L3. See that 0.69897? That's the exponent. So if I say 10 to the 0.69897, guess what you get? 5. That's what that is. So watch that. Here we go. 10 to the 0.69897 gives you 5. Okay? Alright, let's look at the next one. The next one has base 10 to the power of 1 gives you 10. Okay, let's do one more. You ready? Base 10 to the 1.1761 power gives you 15. Okay, so that's where that is coming from. Let me show you that one real quick. 10 to the 1.1761 power gives you 15. Alright, so that's what's happening. Okay, now let's go ahead and do this graphing stuff. Ready? We want to graph. We want to graph. What do we want to look at a picture of? L1 is my x's, which is the fry time. And what am I going to look at on the y-axis? What list? L4 is the log of y's. So we want to look at L1 and L4. So go to your stat plot and look at L1 and go down there and change your y list to, let's see here. Turn your y list to L4. Second L4, zoom 9, and there it is. Does that look similar to what was above, yet straighter? Yes, it condensed it and it straightened it out. So draw that picture. Okay? All right, here comes the number one missed thing. You have to calculate a new line. Because I'm not talking about L1 and L2 anymore. We're talking about L1 and L4. So you have to do a new line. You need a new line that the calculator needs to have in its brain. So let's do that. Stat. Calc. Number 8. Alright. I just hit enter. It's going to give me the L1, L2. How do I get L1, L4?
L1, L4.
Yep. Your X variable first, comma, Y variable second. So L1, comma, L4, enter. that over to calc, limreg number 8. So this is our new equation for the condensed y's. So let's put that in. So we're going to go predicted. What are we predicting? Good. We are predicting log of MC, not just MC. Predicted. That was really good. I'm glad. Oh, maybe. 1.168. Then he only has 4 more to go to make up for it. Minus 0.01899 times Fry time. The R value is negative 0.9932. All right, so look at that. Stronger R value already, right? Am I right or am I right? Look here.
You're always right.
I'm always right. Okay? Next, we want to do the residual plot to confirm that it's a good fit. Our X is still Fry time. What is on the Y-axis? Good. The residuals of log moisture content. Residuals of log moisture content. So you better go put those correct residuals in there because your calculator is thinking of the old residuals. You have to fix them. Calculator's thinking of the residuals up above. So go to stat. Yes. Go over and clear out the old L5. Clear out the old L5. Okay. Yeah. Hey, guess what? Yeah, go up to L5 and hit clear enter. Hey, but how do I know? Since
Oh my God.
Okay.
Deleted L5.
Okay. Listen, one second here. Okay, asking you a question, important question. Why, when I do resid, and I go and on the L5, how is it going to give me different numbers than before? Yay, very good. Because my calculator is thinking of a new line in its brain. That's why if you had not calculated that new line, it would still be thinking of the old line and give you the same answers. Okay? So you know it's wrong if you get the same answers, correct? Alright, no I did not. Alright, so we put this in there. We go up to the L5. Second stat. Number 7. For resid, enter. Okay, there they are. I want to look at the resids. So are you to that point where you know what to do now? L1 and then what? L5. Our resids, my new residuals are in L5. Zoom, 9, boom. Now, it's not perfect, is it? I mean, in my mind, I almost think there's a fanning out happening, okay? So let's put that in there. Okay. So here's the deal. Is this better scatter than before? Is it a stronger R value than before?
Yes.
Okay. Because of those two reasons, you know, this may not be the best choice ever, but we only know of one way. So of the two, this is the better choice. So we're going to say the exponential model is more appropriate. Yes, because it's better than up above. All right. This last thing we're not doing today. We're going to do this right here, which is kind of some logarithm mumbo-jumbo computation, saving that for tomorrow. But for now, I have a few fixes on the homework that I have to tell you. So let's go through that, and then you're going to spend the rest of the class period getting at least one of these done, because you only can make sure you know how to do it by doing it. First fix on number 1. The second number 15, the one that goes with 21, should be a 14. Okay, change the second number 15 to a 14. If you do not, then you get not as good stuff. Okay? Next page. Nothing to fix on that page. Third page. Number 3. This problem is about Halloween candy and the years. I want your equation to have the same y-intercept as mine, so I need to have you put your years in as 1995, 1996, and so on, so that you put yours in the same as mine, so that you get the same y-intercept. Okay, so notate that. Because on number 4, I actually changed it up. Number 4, I did the years as the years past 1990. So for the x variables on that, or x numbers, you're going to want to put 1, 2, 3, and so on for the years past 1990. Okay, one final thing. 3 out of these 4 problems, it is better to do exponential. So the exponential is a better fit than the linear. Still might not be perfect. In fact, the first one kind of looks like it still has a pattern, but it's better. However, I'm going to go ahead and tell you that on number 3, please don't be alarmed and don't forget that if you have got nice scatter in the residual plot for linear, then stop. A linear model is good, and you pretty much then don't need to do this, because if a linear model is appropriate, you're done. So please don't forget in this whole, getting wrapped up in doing another transformation, that it still could be a linear model is the best. Done. So now I want you guys to do that. I'm going to be walking around helping you so that when you encounter calculator errors, I can help you with that.